eruptions so vast, so earth-shattering, they have changed the history of our planet. Climate collapse, toxic turmoil, mass extinction, worse than a killer asteroid or nuclear war. They are Earth's most destructive supervolcanoes. North America. The time was 640,000 years ago, long before humans arrived on the continent. Amid the Rockies, one of nature's great mountain-building projects, vast columns of smoke began to rise high into the atmosphere. And soon a smoky haze wrapped the globe. A thick blanket of ash spread over the western United States. Geologists have traced this event to a depression in the land known as a caldera, in the heart of Yellowstone National Park in Wyoming. Today, we venture to Yellowstone to admire its spectacles of steam and boiling mud. All around, thermal energy is underfoot, like a pressure cooker gathering steam. The heat escapes in an array of smoldering cauldrons, steam vents, and hot springs like the famous Grand Prismatic. Here, superheated water rises up from deep below ground, then cools and sinks back down in a constant cycle. Geysers are powered by boiling water that moves up through constricted channels in the rocks. When enough pressure builds, steam and water escape in jets that can blast high into the air. Along the Yellowstone River, heat welling up from below softened the underlying rocks to such an extent that water released by rapid melting at the end of the last ice age was able to carve out one of the most spectacular river canyons in the world. Visitors to Yellowstone may never suspect they are atop one of the world's largest active volcanoes. The last time it blew, it sent an estimated 1,000 cubic kilometers of dirt, rocks, ash, dust, and soot into the atmosphere. It's difficult to grasp the sheer scale of that eruption. Compare it to recent experience. In 1980, Mount St. Helens blasted out just 2.79 cubic kilometers of ash, less than 0.3% of what Yellowstone ejected. In 1991, Mount Pinatubo in the Philippines released 10 cubic kilometers of material, along with 20 million tons of sulfur dioxide. A volcano twice that size blew up on the Indonesian island of Krakatoa in 1883. It unleashed the equivalent force of 10,000 Hiroshima bombs and tsunamis that killed 36,000 people. The same year, the Norwegian artist Edvard Munch painted The Scream, with a sunset likely inspired by the effects of smoke from Krakatoa. Clouds like blood and tongues of fire, he wrote, hung above the blue-black fjord in the city. This is Anak Krakatoa, or Child of Krakatoa, an island that has risen in the years since. It is a modest but unruly cone that may be building again toward another big one sometime in the future. The modern standard was set by the eruption of Tambora, 8 times larger than Krakatoa, in 1815. In its aftermath, 1816 became known as the year without a summer. Crops failed and livestock died in much of the northern hemisphere, resulting in the worst famine of the 19th century. The public has long been aware of the hazards of an erupting volcano. Explosions, lava, and debris flows, like the ones dramatized in the movie Dante's Peak.
What is that?
That's a pyroclastic cloud.
The record of recent volcanoes, from Tambora to Pinatubo, has added an additional global hazard. In these images captured by astronauts aboard the space shuttle, you can see the sulfurous haze that covered the Earth in Pinatubo's wake. It blocked enough sunlight to send global temperatures down by about 0.5 degree Celsius. Mount Pinatubo erupted at a time when scientists had begun to use high-powered computers to model the response of Earth's climate to large-scale disruptions. Based on their success modeling the circulation of particles from Pinatubo, one group sought to explore the consequences of another type of eruption. Limited nuclear war. They focused on India and Pakistan, 2 countries that were engaged in a nuclear arms race. The experiment assumed 100 Hiroshima-sized bombs. The intense heat of cities burning up sent over 5 million tons of smoke rising into the stratosphere. With no rain at that altitude to bring them down, soot particles lingered for years. They absorbed far more solar radiation than the brighter sulfuric acid particles emitted by volcanoes. As a result, according to the study, global temperatures dropped by 1.2 degrees Celsius, equivalent to the year without a summer after Tambora. That shortened the next growing season by 10 to 30 days, resulting in widespread crop failures. Finally, in 2 to 3 years, the smoke began to clear, and the climate steadily recovered. But those impacts are dwarfed by what would happen in the wake of a supervolcano. Take the last major Yellowstone eruption, 640,000 years ago. Scientists at the Max Planck Institute in Germany used an ensemble of computer models to study its impact on Earth's climate. Their virtual eruption sends up a giant cloud of ash and dust that's taken by high-altitude prevailing winds. In a month's time, the cloud has spread over much of the northern hemisphere. The simulation tracks the bitter consequences. Solar radiation at Earth's surface falls off in an uneven pattern. The darkest point occurs around 18 months after the eruption, with the mid-latitudes of North America and Europe experiencing a steep drop in sunlight. Air temperatures fall too, hitting their lowest point at 18 months. In some places, they fall by an average of 10 degrees Celsius. That leads to the rapid growth of sea ice in the Arctic. More sea ice means that the Earth reflects even more solar energy back into space. With cooler surface temperatures, rainfall levels decline, and oceans and land areas retain more carbon dioxide. These factors all lead to a drop in biological productivity. With food supplies lasting just weeks or days in some regions, human populations would be subject to serious losses. From their steep initial drop, average global temperatures recover gradually, approaching pre-eruption levels only after 2 decades. As powerful as the Yellowstone eruption was, it still does not approach the greatest supervolcanoes in history. This is Toba, a large mountain lake on the Indonesian island of Sumatra. It's the crater left behind by a super-eruption 74,000 years ago. What made Toba super is the sheer scale of the eruption. Over 14 terrible days, Toba blasted 2,800 cubic kilometers of material into the air. That's almost 3 times Yellowstone. Its grim aftermath was a global cataclysm, including a global cold spell and persistent drought. One theory holds that Toba brought the human species perilously close to extinction. What causes a catastrophe on this scale? The answer takes us back to the birth of our sun, around 5 billion years ago. It began in a swirl of debris, likely drawn together by shock waves from a stellar explosion. Amid the chaos of the early solar system, gravity drew clumps of rock and dust and gas together. A fiery young planet formed, molten at first. Millions of years passed. Earth's surface gradually cooled, but its interior remained hot. Add to that heat generated deep within the planet by the radioactive decay of uranium, thorium, and potassium. To this day, heat energy is rising steadily from Earth's interior, a vivid reminder of the fires that burn inside it. The heat makes its way to the surface through a vast middle region called the mantle. It punches through where Earth's crust is thinnest, in the middle of oceans. That causes massive plates that line the surface of the planet to push apart, often flooding the ocean floor with lava. These oceanic plates collide with thicker continental plates. That drives them down into the Earth, along with volcanism's secret ingredient, water. Some rocks, when mixed with water, melt more readily. They form a reservoir of magma deep below ground. As more magma enters the reservoir, the pressure increases. That forces magma up to the surface, and a volcano erupts. A supervolcano, like Toba or Yellowstone, begins with a much larger reservoir of magma. A recent study showed that the larger it gets, the more buoyant the magma becomes amid the solid crustal rocks that surround it. Over time, this buoyant reservoir pushes up on the terrain above it. The rock above the magma begins to break. Channels or dikes form to release the rising magma. The land collapses onto the magma, helping to propel it up and out. The volcano does not so much erupt as it explodes. The thermal features that dot Yellowstone are small in scale, yet they too are fueled by an immense dome of magma deep underground. By tracking the pattern of seismic waves from small earthquakes, scientists have been able to follow it down to its source. A kilometer below, surface water enters layers of heated rocks, then shoots back to the surface in hot springs and geysers. Deeper still, 10 kilometers down, they've located the upper reaches of an immense reservoir of magma. It measures over 100 kilometers wide and 400 kilometers deep. Scientists now believe it's partly the result of the Pacific Ocean plate diving below North America, and partly the product of a hotspot. It's similar to a deep plume of magma that fuels Hawaii's volcanoes. Over the last 16 million years, as the continent of North America has moved, inch by inch, over the Yellowstone hotspot, the volcano has reawakened time and again. The next to the last time, it ejected 5,000 cubic kilometers of material into the atmosphere, almost twice as much as Toba. Toba is known to have erupted at least 3 times in the last 1 million years. There are signs that it's gearing up for another. Some parts of the caldera, including a large island in the middle called Samosir, have risen due to a refilling of the magma chamber. Indonesian scientists recently reported they have detected its presence, starting at a depth of 20 to 100 kilometers down. The volcano is not active now, but it's in one of the most geologically active regions in the world, including the nearby Sumatran Fault and the Sumatran Subduction Zone. This region is known for major earthquakes and a string of volcanoes, including Krakatoa and Tambora. If or when Toba does erupt again, it still won't hold a candle to Earth's greatest eruptions. Roll back the geological clock to a time around 65 million years ago. A giant asteroid slammed into the Earth. It wreaked havoc on the climate and may have led to the extinction of the dinosaurs. The impact coincided with another type of catastrophe. That was a time when today's continents were taking shape. The Himalayan mountains were beginning to rise up, and India had not yet crashed into Asia. In central India, one of the largest volcanic structures on Earth made its presence felt. From the so-called Deccan traps, the Earth literally spilled its guts. Over a period lasting perhaps 30,000 years, 500,000 cubic kilometers of lava flooded onto the Indian landscape. The Deccan Traps eruption was about 500 times larger than the last Yellowstone eruption. An even larger, more destructive event occurred around 235 million years ago in what's now Russia. Back then, all of Earth's land masses were joined together in a supercontinent known as Pangaea. In a period known as the Permian, amphibians and early reptiles flourished. Insects were everywhere. Fern plants, dominant for eons, were beginning to give way to conifers and palms. In the oceans, amid vibrant coral reefs, invertebrates and fish inhabited the open water. Then, in the geological blink of an eye, it was over. For a period lasting up to 10 million years, countless small eruptions generated several thousand times more lava than Yellowstone, spreading over an area the size of Western Europe. What it brought was not volcanic winter, but rather hell on Earth. The atmosphere became choked with carbon dioxide and methane gas. Temperatures around the world soared. The Earth belched deadly toxins, including high levels of mercury. The oceans turned acidic, their waters depleted of oxygen. By the time it was over, up to 70% of all species on land and 90% of marine species had disappeared. Ecosystems around the planet collapsed in what scientists call the Great Dying. And that was not even the largest volcanic eruption in Earth's history. For now, that honor goes to an undersea eruption that began 125 million years ago, creating a plateau 30 kilometers thick called Ontong Java. It released about 100 million cubic kilometers of magma. Scientists believe large eruptions like Ontong Java or Siberian traps occur where broad regions of magma, called large igneous provinces, push toward the surface. The Earth is pocked with dozens of them. They are spread out across all the continents and oceans. Thankfully, these regions have erupted only very rarely in Earth's history. Super eruptions on the scale of Yellowstone and Toba, linked to the movement of crustal plates, are more frequent, perhaps every 100,000 years or so. Because so little is known about what triggers them, there's no telling when or where the next one will occur. Are we due? Scientists at Yellowstone are watching for early signs. Earthquakes, rising heat, the restless stirrings of a planet under pressure. Someday, somewhere, the planet will once again vent its rage. When it does, we can be sure that it will change our world forever.